Hello everybody, welcome back to my channel. Today I want to take us through a paper that talks about building better, building and better understanding visual language models, insights, and future directions. So a couple of days ago, the team from Huggingface released a new paper that talks about their step-by-step approach in building their own vision LLM model. Um, and we're going to go through it and see if there's anything useful that we can learn from them. And look, this is my first time going through this paper, so I would assume that will be the same for you as well. So let's go through it together now, shall we? Okay, let's start off with the abstract before anything else. The field of vision language models, VLMs, takes images and text as inputs and output text. It's evolving and reach consensus on multiple key aspects of the development pipeline, including data, architecture, and training methods. So this paper is a tutorial for building your own vision LLM. We begin by providing a comprehensive overview of the current state of the art architectures and highlighting the strengths and weaknesses of each. And I assume that will be addressing the major challenges in the field, suggesting promising research directions for underexplored areas. We then walk through the practical steps to build ID fix tree 8 billion parameters. A powerful VLM that significantly outperforms its predecessor, IDFix 2, while being trained efficiently, exclusively on open datasets, and using a straightforward pipeline. These steps include the creation of the Dogmatics, a dataset for improving document understanding capabilities, which is 240 times larger than the previously available datasets. And they also release the model alongside with the datasets created for its training. I see. So well done, Hugging Face. I think we should look into what the model that they provide right now. So let's see. Let's go to Google. Let's see. Okay, so it's online already. Okay, so yeah, if you guys are interested in the model, please do check it out on Hugging Face. It's open source and free to use as usual, right? So I will probably check this out after we go through the paper together. Anyway, yeah, cool. So now let's go back to the paper, right? So in this paper, they have the introduction section right here. We should probably go through that first. It's not too long. Okay. So let's see. Vision language models that take images and text as input and output text are highly effective in various applications such as document and figure understanding, solving visual math problems, converting web page screenshots into code. The advancements of open LLMs and vision encoders allow researchers to build these unique model pre-trained models to create advanced visual language models that solve these tasks with good accuracy. However, this paper would highlight a variety of divergent, okay, the keyword is divergent design choices across the development pipeline, indicating a lack of consensus. Right. I, I would assume there's a lot of different approaches, and nothing is like there's no unification in a sense. For instance, while many models have chosen to concatenate the sequence of image hidden states with the sequence of text embeddings before feeding it into the input. The model used interleave transformer based cross attentions. Yeah, if you don't know what cross attention is, I do have a video on that, so make sure to check out my first video, my first video in my YouTube channel for that. But I will assume that you already know that, so let's continue. So yeah, cross attention to fuse the vision information into the LM, just like Flamingo. I think Flamingo is developed by Google a few years ago. Yeah, 2 years ago. These different core choices in the model development is not ablated nor justified, making it challenging, right? So no one has tried to do some kind of like ablation to see whether or not these design choices make any sense in terms of accuracy. So, in this paper, we begin by guiding the reader through the main questions in the field, offering a detailed overview of the latest vision language models approaches to address these challenges, along with the strengths and weaknesses of each. So, we will focus on the various architectures used to connect, okay, you see, to connect pre-trained language models with vision encoders, okay? And secondly, the different types of data employed. Okay, the different types of data used in vision language model training, their utility, and the typical stage at which they're introduced. The training methods for the models are often divided into multiple stages. Okay, so it's multiple stages. Huh? Okay. Finally, the challenges encountered. Right. So the challenges encountered in evaluating the models, and I propose some future research directions, particularly around the data to make the model more accurate. Okay. So, right. Building on this interview, we will then walk through the practical steps for building IDFix tree, right? Their open source model using open data sets and a simple pipeline. The model outperforms IDFix2, its predecessor, in document understanding tasks, right? To boost the capabilities, right, they created a new dataset, I believe, called Dotmatics dataset, and it has 2.4 million images and 9.5 million question and answer pairs derived from 1.3 million PDF documents. Right, so it's a pretty large scale data set, right? And they release their model and the data sets along with it. All right. Before we do that, I want to check out their data set. Let's see. Okay, right. So here's the data set, right? Yep. So let's take a look at some samples of their data set here. So let's see. Okay, so the user asks, what is the main topic of the question? And the assistant says something about it. Let's look at it. Okay. I see it now. All right. All right. So the data set is available. Don't see any issues in there. That's good. So let's see. What I like to do in my videos is that even in my own personal reading time is that I typically go straight to the conclusion and see if there's anything that I can any new information, right? So let's see. Okay, in this paper they provided a comprehensive tutorial on vision language models, emphasizing how important architecture data and training methods are. And then they also provide an in-depth analysis, right? I think we should go through this part, the in-depth analysis. And then they highlighted the strength and weaknesses of different choices of the design and some potential research direction. Okay, so now that's the conclusion. I think it would be cool if we can get to it, get to the main meat of the paper. Okay, cool. Let's start with the first part right here. Analyzing architecture choices in vision language models. Okay, subsection 2.1, connecting unimodal pre-trained models. Okay, since the introduction of Frozen and Flamingo, okay, I'm not too sure what Frozen is, but I assume it's similar to Flamingo, right? So let's see. Most VLMs have been built on top of unimodal pre-trained backbones, a language model, and or vision encoder. Okay, so if you don't know what this means, I would assume it would be something like this. If you take a look on the right hand side of the screen, let's say if you have a GPT model, right, and this is the output text that you want to produce. Now, typically what you want to do, right, if you want to use an image encoder, is that you have the encoder sitting right here, and it produces a set of tensors, which then you can feed in as part of the input sequence. So you have the image, you feed it into the encoder, and then you convert it into a set of vectors, and then you feed it back into GPT. And on the other hand, right here, this could be your Q&A text right here. And you're kind of doing like auto regressive training. So that's not too complicated. And the visual encoder is usually, I believe, it could be vision transformers or even convolutional networks. Anyway, let's move on. Yeah. So, okay, a language model and or vision encoder rather than training entirely new models from scratch. Okay, the availability of open source models and image encoders are expensive. Uh, okay, right. It enables researchers to use those models to create a hybrid, right? VLM. Okay, so the two things are either connected with a cross attention or a self attention architecture, which you can obviously do in between in this part, right? Yeah, you can either use a self attention or a cross attention. Well, for me, I typically use a cross attention mechanism, but it might change my mind. This paper might change my mind. Let's see. All right. So cross attention architecture. The cross attention architecture is introduced in Flamingo. The image hidden states encoded by vision backbone are used to condition the frozen language model using freshly initialized attention cross attention layers that are interleaved between pre-trained language model layers. Right. The key values in these layers are obtained from the vision features, where the queries are derived from the language inputs. Okay, right. There's a lot to unpack here, right? So they're talking about cross attention, right? And the image hidden states encoded by the vision backbone, like here, like this part right here, which I talk about the vectors that the vision encoder produce are used to condition the frozen language model using freshly initialized cross-attention layers that are in between the language model layers. Right? The key values and in these layers are obtained right, from the the image hidden states. What this basically means is that if you can recall the attention mechanism is something like this, right? It's QK, and then you have the softmax applying to the Q and K product, and you apply a softmax operation to it. That's transpose into K, right? And what you do in this case for cross attention for the image part, you feed in the image vectors, right? into the K and the V, right? And I would assume this is the original LM vector. Anyway, yep. So while the queries are derived from the language inputs, right? In practice, a cross attention block is inserted after, okay, after every 4 transformer blocks. All right, so it's roughly adding like a quarter more parameters of the original LM size. So, so obviously, right? Obviously, the more parameters you add, the better the accuracy would be, intuitively, allowing it to reach strong performance without having to fine tune the entire LLM. Therefore, you can preserve the performance of the LM, right? So, okay, right, there's a whole bunch of models that did that open sourcely. So let's see, okay, that's cross attention. Now let's move on to self attention. Okay, in the self attention architecture, introducing a blip to, okay, um, the output of the vision encoder is treated as tokens. Okay, so it's treated as tokens and concatenated to the sequence of text tokens. The entire sequence is then passed as input to the language model. Okay, so it's kind of like this diagram that I wrote back at the beginning. You have the vision vectors, right? And you have the query and answer text, and we fit it together as an input sequence. This is exactly what this is saying. Okay, the sequence of visual tokens can be optionally pulled into a shorter sequence, making the model more efficient, right? Basically, a compression in a sense. We refer to the layers that map the vision hidden space to the text hidden space as modality projection layers. Okay, the layers that map the vision hidden space to the text hidden space. Okay, right. Figure 1 highlights the different components of self-attention architecture. Okay. Okay, and I also say that most recent VLMs have adopted this self-attention design, such as Lava, Quen, VL, DeepSeek, Spink, Villa, Mini Gemini, and MM1, Intern LM, and so on. Okay, so as you can see, figure 1, this is exactly what I was talking about. You start with the image, right? So this is for self-attention, right? You feed it into a vision encoder. You get the hidden state vectors representing, I don't know, each patch of the image. You can do some kind of modality projection, maybe some kind of pulling mechanism, and then after that, you feed it into the LLM. And I would assume that there could be some, and I assume that this vector that comes from the text could be like a separation token. It's like it, it really depends though, but we shall see. So okay, right. Let's see what the caption says. The self-attention of fully auto-regressive architecture. Why is there a comma? Anyway, input images are processed by vision encoder, and and the visual features gets mapped to the input sequence. They are concatenated within the input sequence. Yeah, that all makes sense. Okay. Another question is, which approach works the best, right? So, okay, the performance comparison between these two main architectures was explored. Okay, so it was already explored in a recent paper. The pre-trained unimodal models are Mistral 7B for LM and SIGLIB for the vision encoder. The model with the self-attention architecture has a total of 8.3 billion parameters, including almost including 740 million new parameters. Right. Mm, yeah, well, the model, okay, right. So for the one that uses self-attention, it's 8.3, but for the one that uses cross-attention, it's 10 billion parameters. So, and the authors demonstrated that the cross-attention architecture significantly outperforms the self-attention mechanism architecture when the backbones are kept frozen. However, when parts of the vision encoder and language model are trained with LoRa, adding additional, okay, right. So when if you use low rank adaptation, I guess, to fine tune the entire architecture, okay. So okay, the cross attention architecture performs worse. Strange. All right. Nonetheless, this study did not evaluate the performance of vision LMs on text-only benchmarks. Okay, right. So it's only testing like vision, but not text. All right. Intuitively, when parts of the language model are unfrozen, right, we need to incorporate data from the LM data mixture into the VLM training data to maintain performance. Okay, that's true. Because if you only train, right, if you fine tune the entire LM, right, but you fine tune the parts of the original LM on the vision language tasks, you still need to incorporate some of those text only tasks data into the training set, because otherwise the LM might forget its its text task abilities, right? We call this a catastrophic forgetting. There's a unique term for that. So yeah. I was wondering if it's possible to like combine like self attention and cross attention together, right? It seems to me that if you do this, if you combine those two things, maybe the accuracy would be higher. Because if you think about it, right, it's directly compatible. Like, let's say if you have like 4 layers, and then you have your cross attention, which I call CA, and then you have another 4 layers here. So, but at the same time, you can have the image encoder, right? You can have your input sequence be a combination of the text and the image information as well. So maybe this could work. I don't know. Yeah. But if this is a research that you want to go along, maybe this could be a new idea for you. Mhm. Yeah, yeah. If you do this kind of idea, please make a citation to my video. Yeah. Anyway, yeah. Moving on. 2.1.4 Impact of the pre-trained backbones on performance. Okay, so there's a lot of studies that found that the performance of each standalone unimodal pre-trained backbone correlates with the performance of the resulting VLM. Hmm. Well, yeah, absolutely. Absolutely right. So you need to have a good image encoder and you need to have a good large language model in order to create a good vision language model. It all makes sense, right? So let's continue. For instance, the authors demonstrate that replacing the model from Llama 1.7b with Mistral 7b leads to a substantial improvement across benchmarks. For example, right, going from 35% on MMLU and uh, and it goes to 60.1% when you switch the model to Mistral, right? So that intuitively makes sense. And if you check out the image encoder, I believe it's image encoder. If you replace the vision transformer, right, the clip vision transformer with a SIG-LIT, uh, the, the performance on ImageNet goes up from 78% to 83%. And again, it makes sense, right? If you have a bad vision encoder, right, then it basically like forces the LLM to understand. It is like having a bad eyesight, right? You can't do much with rubbish information, right? So, okay, and to say, because the vision encoders are often trained on different datasets and optimized for various tasks, some models like Swings combine representations from multiple encoders, such as Dino V2 and Clip, to create better visual embeddings. But it's expensive, obviously, using multiple encoders. So yeah, recent research have been focused on improving open language models. There's a lot of papers here. In contrast, a few open vision encoders have been released, right? And so far, as of in the time of the paper, right, SIGLIT as a 400 million, standing out to be a favorable, having favorable performance to parameter ratio. So there's obviously a need for better vision encoders, open source. Yeah. So okay, right. And this one is interesting. And to say, is a vision encoder really necessary? Hmm, I never thought of that, but let's take a look. Okay, instead of employing a vision encoder, Fuyu feeds the image patches directly into the language model after applying a set of linear projection to adjust the dimensions. Okay, now this is this is the most straightforward way, right? So it's like directly treating every single patch as if it's a text token. Let's see how they do it. Right. Okay. Yeah. This approach offers two main advantages. Firstly, it is independent of another pre-trained model. Basically, you get all the information from the original image, and you don't have to bottleneck yourself with respect to the image encoder that you're using. Fair enough, right? And the other point is that the original image details, right, might be necessary for accurately responding to the prompt, right? For example, right, and this comes from one of my experience, is that sometimes just by like adding in like, yeah, do you know how like in convolutional neural networks, right? And you have like layers of like a max pulling and mean pulling, right? And all this operation is basically trying to focus on specific aspects of what that thing is to be the important information, right? But the issue is that it will be discarding out every other information that could be useful for the LLM. So this approach kind of makes sense from that point of view, right? Okay. On the other hand, a pre-trained vision encoder transforms an image into a representation that is independent of the user's prompt. As a result, vision encoders aim to capture as much information as possible, but can still miss the important details for the LLM, like I say. Okay, so WISP Focus attempts to address this drawback by incorporating the user prompts into the vision encoder. But this approach is less natural in interleave image text conversation, where prompts maybe refer back to the previous question. So this risk-focused approach is less flexible, probably even not that good, to be honest. All right. So there's a lot of advantages, right? But with this simplistic approach, but the truth is that although intuitively it makes sense, but reality doesn't really necessarily say the same thing. In fact, the full use architecture is not doing that well on the benchmarks when compared to similar size models released at that time. Okay, so but this approach isn't given up yet because Polygemma also experimented with this approach and reported a notable drop in performance when not when compared to using a pre-trained vision encoder, right? And they suggest that bypassing a vision encoder pre-trained on billions of images can lead to longer times to achieve similar performance. And then again, right? It it also comes back to like the inductive bias that the vision encoder already has, right? If you are just going to feed in the image patches directly into the LM would need to relearn, right? Relearn, learn how to understand images from zero. So yes, it is simpler, but you're really getting more simplicity by sacrificing the training time. You're basically going to need to train for longer or maybe even more images than you need. So anyway, yeah. Furthermore, handling image representation within the language model might decrease its performance on text-only benchmarks. Exactly. Even if this approach outperforms others on multimodal, most VLMs are not evaluated on text-only benchmarks, making it unclear whether or not the vision encoder affects the text benchmark at all. Right? And finally, this approach has not been tested yet with an effective pooling strategy that does not significantly reduce information by operating directly on raw pixels. Looking ahead, for tasks like video understanding or extension to other modalities, it will be important to develop an architecture that can effectively reduce the number of visual tokens passed to the language model to maintain a reasonable context length. And again, the more visual tokens you use, the slower and costly the language model inference is going to be, obviously. So another question is, how should we connect the vision encoder to the language model? Right? Many models use a simple linear layer between the vision encoder and the LM. It all makes sense, right? Hmm. Hold on, let me just check. How many more do we have? Yeah, okay, right. They use a simple linear layer to ensure that all encoded visual information is retained since no pooling strategy is applied. Uh, but this is very costly, obviously. So, yeah, okay. Quen reduces the number of visual tokens by using a one-layer cross-attention module between a group of embeddings and the image hidden states. Similarly, IDFix2 employs a cross-attention module within a perceiver resampler. Not so sure what a perceiver resampler is, but I don't think we need to know this in order to continue. Okay. And to demonstrate that the number of visual tokens can be compressed to up to 64 divided by 77. while maintaining performance, except those requiring extensive OCR capabilities. I mean, this already makes sense, right? OCR is a difficult task. It requires very minute details of the images. When you're doing this kind of like pooling, aggregation operations, right? You tend to lose a lot of information. Anyway, yeah. InternLM also shows that increasing the number of visual tokens per image is necessary for benchmarks. Focus on OCR, same thing, right? Okay. Despite the efficiency of perceivable resampler, okay, right. We need to know what a perceivable resampler is. Otherwise, if I keep on mentioning it, we won't really know. Okay, let's see. Okay, Weights and Biases has an article about it. Hmm, yeah, so let's. It will take a while. Okay, it's loading. Okay, cool. A perceiver. Let me see. A perceiver. I'm trying to control F here. Oh, come on. Hmm. Looks like it's not letting me search. Okay, it's. Huh. Okay. Well. Okay. Maybe not this website. Maybe this one should be okay. Okay. Perceiver resampler cross attention capturing. Does this say anything? Okay. Resampler. Does it say much? Does it? Okay. Yeah. Let's see. Perceiver resampler. Mm, okay. So there's another paper, obviously about the perceiver architecture. Oh, yes. Yes. Okay, now I remember. Right. So the perceiver architecture basically means that, oh well, you have this like randomly initialized, they call it a byte array, but it's more like a learnable set of vectors, right? And then you feed it as the key and the vector, and you have your, oh, sorry. Mm, no. Yeah, it's it's fine. So basically, this entire architecture. Wait. Okay, no, sorry. Yeah. So this is your original input data, right? And this is your randomly initialized tensor. And what you want to do is that yeah, in order to save computational costs, you have a small, if I'm not mistaken, you have a very small latent array. And what you do with this cross attention um, modules is that you hope to like contain the information from the input data and also getting processed by the transformer architecture, and this saves computational costs. Right? So that's what they are trying to do, I think, but I'm not too sure about the resampler part. But I think we shouldn't cover too much about that. Okay, the perceiver resampler and its use has been challenged in several papers. Okay, right. It is suggested to use the 2D structures of the images more effectively. So some of them introduce a C abstractor, which introduces 2D positional embeddings to the visual features, followed by ResNet. In .owl, H reducer is introduced. My goodness, there's a lot of these aggregation approaches. Using collisions to divide the number of hidden states by 4. And InternBL achieves a fourfold compression by using a pixel shuffle strategy. We're not gonna cover all of these, obviously, since that's not the main thing, but you can check it out yourself. Okay, so, okay, right. And now next, the image splitting strategy, a trick to increase the number of visual tokens. Okay, and I assume this is important, right? So let's go through it quickly. Okay, introduce a new reader in Sphinx. The image splitting strategy involves dividing an original image into multiple sub-images. Okay, each which is encoded separately by the visual encoder. Okay, encoded separately. The number of tiles can be fixed, such as consistently using 4 crops per image, or it can vary depending on the original resolution, with the image split every n pixels, for example. Okay, isn't this just splitting into patches in some sense? I'm not so sure. Okay. When the number of tiles is based on the original resolution, the model is trained with varying number of visual tokens. This approach is good during inference. For Okay, I see it now. For simple tasks, you need to use fewer visual tokens. Something that's not like uh, OCR, right? That's not OCR, right? While more computational resources can be allocated to OCR, that requires more visual tokens, right? And this way, it's kind of like adaptive computation in some sense. Hmm. But I still think that it's kind of like I don't know. It's not that elegant in my opinion, because it's like, how do I say? You Let's say if I have like a new task, right? A new task, and and you wouldn't really know, especially in like critical situations, right? You you don't really know how much visual tokens you need unless you already have experience on that task. So I'm not too sure about this approach, but anyway, most vision encoders are designed for low fixed image resolutions and not suitable for those. So yeah, you can use existing vision encoders and feeding in smaller images instead of the original big image. Okay. However, since the tiles are not independent, encoding each one of them separately can be suboptimal. Exactly. But the strategy involves adding the downscale original image to the list of tiles, resizing to match the resolution. Hmm. Yeah, you can retain some of the global information, but obviously you do get the reduced information from the reduced resolution. Uh, so, and they asked the question, can we do better than that? Right? So, instead of splitting up the images, how about if we can get an encoder that natively process images of varying resolutions? Hmm. Isn't that kind of like a UNet, for instance, where you have multiple resolutions and you process them? Okay, including the very large ones without changing the aspect ratios, potentially incorporating mechanisms for long context efficiently. This model could be trained using the patch and pack strategy. Okay, cool. Strategy, there are a number of visual tokens per image based on the original resolution, enabling the entire image to be encoded without the need to crop it into multiple smaller images. Okay, so I guess This entire thing is the research question, right? Right. And I believe some of you viewers might be interested in solving this. Hmm. I would say that this problem will, yeah, it will require some intuitive approaches, but I also think that there's not much that you can do, honestly, though, but we shall see. Okay, now let's go through this part right here. Training methods and data sets for vision language models. Let's see, how many more parts do we have? Okay, all right. I will cover through this part and the challenges. Okay, let's go. See, how many more do we have here? There's a lot of things in here, but I think what we should do is to go through this section uh, quickly. Okay, let's go. Training vision language models involves multiple stages, primarily due to the limited availability of high quality data at scale. Okay, high quality data at scale. Okay, there's not enough high quality data, and obviously memory constraints, stability issues, right, during training, right? Okay, so during these stages, right, you start off with a bad quality data, and then you progressively introduce better quality data. Okay, the maximum image resolution is gradually increased and more model parts are unfrozen. Okay, interesting. Right, so this is the arrow pointing towards this kind of trend, increasing image resolution and unfreezing. Hmm, okay, so starting off with introduce documents, image to text pairs, and then stage one data, PDF, stage one. Wow. So you basically have to like add in more data into it in with yeah, in conjunction with the previous data from the previous stages. And then after that, you do some kind of a supervised fine tuning, right? Whether it be on academic data sets, conversations, or alignment data, all up to you. So this multi-stage is pre-training. Now let's take a look at it. Okay. So multi-stage pre-training. Okay, right. The primary goal of pre-training is to align the backbone models and train the newly initialized parameters. Okay, so yeah, and they say that this can be achieved using large-scale data sets to expose the vision language model to a variety of examples to improve its knowledge and robustness against OOD data out of domain, right? So to preserve the LLM capabilities, initial capabilities, they start by freezing the backbone models and focusing only on the newly initialized parameters until when you reach a certain performance level, right? And after that, they gradually un- unfreeze the vision encoder or the language model or the language model, right? If there's any stabilities or there's a need to improve its accuracy while adding more regularization, then then the full unfreezing approach can be effective, right? So you gradually add in more data, more high quality data, and you also gradually unfreeze components of it. So that's the approach. So yeah, from the start of the training, you keep the resolution really low, and after that, you increase it more and more. And once it's sufficiently high, datasets such as PDFs can be incorporated. So this would be the last step of the training. Okay, that is interesting. Right. In the following paragraphs, they will discuss about the data that they use. I'm not so sure if I want to cover this though. Okay, let's go through it briefly. Okay, image text pairs. Yeah, you can go through some of these, but I'm just gonna highlight some key points here. The text is often noisy, not correct, very short, or challenging, and making training challenging. So yeah, there's like synthetically generated captions to create the data set. Then again, model collapse might happen if you do too much of that. So a lot of efforts are on generating high quality captions for given images, but less is focused on selecting good images. Okay, and this is a good research direction right here, as they say, right? So the future, right? And this is what you could do as well, my fellow viewers, right? So, okay, this is important given the high proportion of web images that are not useful. That's true. Just imagine going to Bing or Google and you will probably see tons of that. Okay, right next, interleave image text documents. So these are web documents, first introduced in Flamingo, blah, blah, blah. Okay, and there's some advantages to use web documents. First of all, you can enhance its in-context learning capabilities. Try to make it to read the text from the images. Okay, and it improves its ability to understand arbitrary number of images within the text, and it exposes the model to a wide distribution of text than what's available in standard image text pair datasets. Okay, right, and that's that. Let's look at PDF documents. So PDF documents, right, so both datasets are extracted using OCR, which can be later. Let's do that. Yep, there's nothing much there. Okay, synthetic data. Okay, I don't know what SH is, but anyway, yeah, image captioning, blah 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 blah. Okay, these datasets are abundant uh, for short and usually requires. Okay, right. So these datasets doesn't address many tasks that the users need, such as document understanding or visual map understanding. Relying on generalization on small dataset is difficult, obviously. So, okay, so so synthetic data can be an approach to fix that. So, given the recent advancements, which in VLMs, they can solve many real-world examples with good accuracy. Creating and training on large synthetic datasets is the logical step. These datasets can be tailored to include examples that closely resemble the user's tasks that likely request, making them more relevant than the data used in the earlier training stages. All right. So let's see right here. Okay. So there's a few categories. Image captioning. The leading data set for images paired with detailed captions is that. Okay. Real world visual Q&A. Text reading in natural images. Text transcription, document understanding, chart understanding, table understanding, reasoning with caught, chain of thought. Okay, let me see. The authors develop a separate data set to enable to answer using COT. They've been collecting charging Q&A pairs. Without that, they employ Claude tree to generate detailed comprehensive rationales. The rationales are filtered with GPT-4V to ensure the quality. Okay, visual. Okay. Right. Even the most advanced struggle with complex mathematical reasoning. Generating synthetic data directly from a teacher model is problematic because the teacher fails to provide correct answers. Instead, these data sets are created by augmenting small, accurate academic mathematical data sets using LMs. In alpha geometry, the authors train a model exclusively on statically generated geometric problems. Right, so you have a system that generates these problems, which then you can use it to train the LM. Okay, next. Converting web screenshots into HTML code. All right, let's see. Instead of software purpose, specialist LM fine-tune for HTML. Okay, right. Let's read this one more closely. To develop models capable of converting web screenshots into HTML, website introduce a Boolean syntactic data of HTML code and the corresponding screenshots. The HTML code was generated using DeepSeek Coder, merged into a single file, then filtered and rendered to obtain the web screenshot. Right. So I guess the point is they use a LM to generate a bunch of random HTML code, and they run the HTML code to create the web screenshot images, and then they can train the vision language models using the pair of web screenshot and the HTML code. That's pretty ingenious. And finally, locating objects in an image. Okay, determining the exact positions of objects for the image. But right. So how do you do that? Well, okay, let's see. So in Blip Tree, what they've done is that they create the large-scale grounding datasets by using a lot of images, and the objects and their location are identified by open world image tagging and object detection models. So basically, you have these specialized AI models, right? These computer vision models that detect the position of the objects and that tag it to create a bunch of data set, a bunch of data, and then you can train the VLM on that. So it's kind of like transferring knowledge in that sense. Okay, now we have reached fine tuning. All right, let's see how much more do we have here. Okay, I might have to stop soon, but let's see how much more do we have. Okay, let's go a bit more faster. Hmm. All right, let's go. Similar to the approach used with LMs, fine-tuning is basically done with supervised fine-tuning and alignment phase, typically PPO or direct policy optimization. Anyway, okay, which dataset should we use for SFT? The literature offers many of them, but they are too small. So okay, right. You see, so there's this dataset called the Cauldron, which has a collection of high quality datasets of many different tasks, Q&A, counting, captioning, and so on. You can check it out after this video, but I think, but the main problem is that the academic benchmarks like these ones, their answers tend to be concise and it can generate similarly brief responses. which could be less appealing to a lot of people, right? So let's see. Okay. And the alignment phase. Okay, so the alignment phase, as as usual, reinforcement learning from human feedback. So yeah, I think this is already covered a lot of times on YouTube, but and a lot of papers. Typically, you would use something like DPO to align the model to behave what you want. All right, and that's that. And now let's take a look at some challenges in evaluating vision language models. Open-ended and multiple choice benchmarks. Let's see how long is it? Okay, so I think this is pretty insightful. Yeah, I'm gonna cover section 4 right now, and we shall conclude then. Okay, so okay. The earliest and most popular multimodal benchmarks are mainly open-ended. Okay, they rely on specific ground truth answers, so even minor variations to its responses is incorrect. Right, it's very strict. So the evaluation method tends to favor models that produce answers closely aligned with the benchmark's expected format. And that is true, right? Okay, right. Okay, right. So yeah, that's that point. So a way to fix it is to perform few shot evaluations. So, uh, but this approach is less effective than training on the benchmark dataset and is not currently used for evaluating instructive models, obviously. But yeah, and also the level of ambiguity in these evaluations can vary benchmark by benchmark, right? So each of them can be different. Each benchmark can be different in terms of ambiguity. So okay, right. And recently, there's this lab metric that asks an LLM to evaluate whether the response generated by the VLM is correct given the ground truth and the specific question. Okay, yeah, I thought of this approach before a year ago, but it kept coming to my mind that what if the LLM that's evaluating the answers is not correct in its evaluation, right? Wouldn't that be kind of risky in general? I don't know. Maybe I could be wrong, but let's continue. Another way to reduce ambiguity is to use benchmarks that include multi-choice questions. Yep, MCQs, right? So in this way, you clearly know how intelligent the model is without, without going into this ambiguity problem that we talked just now. So there's not really a clear answer, right? Because this approach is kind of like hand wavy avoiding that issue. But yeah, but I think this could be another research question, right? Another research question that one of you could look into. And next, challenges in model evaluation during pre-training stage. There is a significant discrepancy between the performance of VLMs at pre-training versus at fine-tune versus after fine-tuning. Okay, all right. So IDFix2 scores of 57.9 on text VQA and less than 55. Okay, but after fine-tuning, it scores 70.4 in the zero shot setting without employing the image splitting method. As noted, okay, right. One reason behind this gap is that the model only starts learning the specific tasks of the visual Q&A during the fine-tuning stage. Right, so it's learning all the prerequisites of image tasks, but it's not like knowing what to do with it, right? It's just standing by, right? Unless the offer more examples more aligned to the ones present in benchmarks. Okay, so when instruction data is omitted during pre-training, more complex tasks like document understanding may perform poorly. So if you don't have the instruction data during pre-training, tasks like document understanding is not going to be good, right, for your vision language models. So yeah, so it's kind of hard, you see, right? Okay, right. In Anifix 2, the authors found no noticeable improvements during pre-training when using 128 visual tokens instead of 64. While this is true for most tasks, the benefit of using more tokens is apparent in optical character recognition (OCR) tasks after fine-tuning with that, with image splitting strategy. So, okay, so this is their suggestion, right? To obtain more accurate insights during ablations, we recommend incorporating instruction data into data mixture, right? And lastly, we have this one right here. So, risk of contamination and over optimization. Okay, and again, this is a really problematic thing going on in open source models, right? Is that you look at the benchmark, it says that it's better than that, but when you actually use it, it's actually worse in a lot of ways. So let's see what Hugging Face has to say about this. So some benchmarks are derived from the validation and test sets, right? So okay, right, and I found that at least 6.6% are right? They're quite identical, right? So there's a similarity even in like the fine tuning stage, and uh, a lot of them, right? The benchmark and the fine tuning, they have like overlapped questions and answers. So so obviously, right, right. So obviously these imperfect benchmarks, right? They should be used to evaluate the performance. You don't use them to train, obviously. And I hate this so much, right? It's like, it's not fair, okay? It's just not fair. Anyway, yeah, and the suggestion is please be honest, okay? Don't cheat. Right? If you cheat and if everyone is cheating, right? The research is not going to progress. Okay. Anyway, all right. So aside from that, let's see. So let's, yeah, I think we have reached this point that I might as well talk about this. Should I? Mm, well, there's a lot of details here, right? So okay, right. Okay, yeah. So let's see. The texts are about the same from what I can tell, but I think I should wrap it up here, right? So yeah, I hope you and I learned something useful from this experience. Hmm. I would say that yeah, the paper is kind of long, but it doesn't really have like much newer ideas aside from what I already know. Maybe perhaps the new one, right? The new idea would would be something more on the synthetic data, but then again, I kind of already knew that's gonna happen. And like maybe this training approach, But anyway, yeah. Uh, yeah. So yeah. And please go check out their data set and their model. Yeah, I haven't covered the model architecture that they use, but yeah, I hope you have some time doing that. Yeah. All right. Thanks. Bye. Oh, and make sure to like and subscribe if you can. It would really, really, really help me out here. Yeah. See ya.